Okay, everybody, it's on to eliminations, which is the last section of chapter 7. So let's go ahead and start sharing. Okay, we talked about substitution, SN1 and SN2 mechanisms for substitution. Now we're going to talk about beta elimination. So this is beta elimination. Beta elimination. Removal of atoms or groups of atoms from adjacent carbons. These are those beta carbons to form a carbon-carbon double bond. Remember, these eliminations are opposite reactions to the additions that we learned in chapter 5, right? So one type of beta elimination is dehydrohalogenation. If I took an alkene and added a halogenation, right? If I took an alkene and added HCl or HBr, I would get hydrohalogenation. Now I'm talking about dehydrohalogenation. So again, this is the bond that's going to break, right? But so is this one. This is my hydrogen. It's on the beta carbon. The carbon that bears the halogen is the alpha carbon. I'm going to eliminate, right, minus HCl or HX. Sorry about that. And what I get is my alkene. And we're going to talk about the mechanism of this elimination. Notice I also get the protonated form. This would be the conjugate acid of the base. And then this would be the salt, whatever the counter ion is for the alkoxide, the base. That would be sodium, potassium, whatever, and then whatever halide. So sodium chloride, sodium bromide, sodium iodide, whatever that would be. Okay. Now, we alluded to this when we talked about stability of alkenes. This is beta. There is regiochemistry here. In this elimination reaction. Eliminations will follow something called Zaitsev rule. The major product of a beta elimination is the more stable alkene. Now remember, based on the heats of hydrogenation that we studied in chapter 5, the more highly substituted alkene is actually the more stable alkene. And when I can have cis-trans isomerism, when that is possible, the trans isomer is more favored. So let's look at these examples. Here's my alpha carbon. I have 2 beta carbons. This beta carbon and this beta carbon are equivalent, so I'm not going to go over that. But I have this hydrogen, right? And if I remove this hydrogen, the HBr here, I'm going to form the double bond there, and I end up with this product. Notice that these are hydrogens. Those are carbons. So this is di-substituted alkene that's formed. Now, if I go the other way and I eliminate the hydrogen here with the bromine, right? So this guy, I'm going to form the double bond here, which is this direction. This is going to be a tri-substituted alkene. This is going to be more stable because it's tri-substituted. So this will be the major product. This would be the minor product. this is the Zaitsev product because it follows Zaitsev rule, where the more highly substituted or more stable alkene is formed. So let's look at another example. Again, I'm going to have this alpha carbon or the beta carbon, which is the same as this. So these two are equivalent. These are equivalent. And then I have this guy. So if I look at the elimination here, I'm forming the double bond there, which is, I have two hydrogens. This is di-substituted. And then if I form, again, this hydrogen and this hydrogen are equivalent. They give me the same product. So I'm just going to look at this side, right? And that's going to be this double bond that forms. This is going to be 1, 2, 3 alkyl groups, 1 hydrogen. So this is tri-substituted, which is more stable, the more substituted alkene. So this is going to be the major product. And this would be the minor product. If you go on to take organic 1 and 2, you're going to find out that this is also called the Hoffman elimination or the Hoffman product. And there are actually ways that I can manipulate my reagents in order to give me that least substituted alkene. The great thing about organic chemistry is if something doesn't happen under certain conditions, I can usually find conditions where it does happen. And the reason I can do that is because I can manipulate what I know about the chemistry of these compounds and chemistry in general in order to design a set of conditions that, according to chemical principles, will give me my desired product. That's a whole hallmark of organic synthesis. Okay, there are two mechanisms for my beta elimination reactions. I have the E1 mechanism. And again, this is going to be stepwise, where I break the carbon-oxygen bond first, and then I react with base to break the carbon-carbon bond. This is 2 steps. I undergo through a carbocation intermediate. So this is very similar to SN1. And it's also similar because the reaction kinetics only involves the concentration of the alkyl halide, which is the rate determining step. So this goes through a carbocation intermediate. And then I also have the E2 mechanism, which is the other extreme. This is concerted. So this is 1 step. The bond making and the bond breaking actually, or the bond breaking, which in this case is the CX and the CH, is concerted. And again, very similar to SN2 in that the RX and the base concentrations are involved in the rate determining step. So again, there are some similarities in these mechanisms between the SN1 and the SN2 and the E1 and the E2. So let's look at the E1 mechanism. So step 1, I'm going to break a bond to give a stable molecular ion. So this is also loss of a leaving group, right? These electrons are going to go and end up with this carbocation intermediate. This is slow, right? It has a higher energy of activation in the first step. This is step 1, formation of carbocation. And then step 2 is going to be elimination. So only secondary and tertiary carbocations are ever formed in E1 reactions. So again, I'm not forming primary or methyl carbocations. They're so unstable that they don't form. Step 2 is a proton transfer reaction. This is going to act as a base, and I'm attacking the hydrogen, and then these electrons come in order to form this double bond. So I'm taking away the hydrogen. Those electrons end up to be the electrons in the pi bond. And then this is going to be fast. So when I have proton transfer from the carbocation to a base, in this case it's methanol, which also is the solvent, I'm going to get the alkene as my product. All right, let's look at E2. This is my one-step mechanism. All the bond breaking and all the bond forming steps are going to be concerted. So simultaneously, I'm going to take a proton away and break the bond where the leaving group ends. So my base comes and takes this proton. These electrons form the double bond, which kicks out the leaving group. All that happens in one step, and I end up with the double bond, which are these electrons here, and I break the bond to the bromine, and I take these electrons and form the double bond. So I end up with the conjugate acid of the base, the alkene, and the leaving group ion. So concerted, I have simultaneous reaction here. Okay, so just like we did with SN1 and SN2, I can actually summarize what's going to happen based on the substrate. If I have a primary alkyl halide, E2 is favored, E1 does not occur, and that's because my primary carbocations are so unstable that they are never observed. Now, this is a little different. Secondary alkyl halides will undergo E1 if I have a weak base. So my weak base can be water or alcohol, and what I'm going to get is an elimination reaction that proceeds through the E1 mechanism. However, if I have a strong base, such as hydroxide or alkoxide, I'm going to get elimination, but now the reaction is going to proceed through E2. So E1 happens with weak bases, E2 happens with strong bases. If I have a tertiary, again, if I have weak bases, I'm going to go get elimination and it's going to go through E1. And if I have strong bases, I'm going to get elimination when it's going to go through E2. Now this is different from the substitution sequence because tertiary only underwent SN1. Here, tertiary can undergo elimination through both the E1 and the E2 mechanisms. The mechanism that's favored is going to be dependent on the strength of the base. So one major difference between predicting elimination and substitution reactions. Now, to confound things even greater, substitution and elimination is often a competing process. And this is because many nucleophiles are also strong bases. My OH minus, my OR, or my RO minus, my hydroxide, my alkoxide, those are great nucleophiles. They're really good nucleophiles. They're negatively charged. They're also really strong bases. So my substitution and my elimination reactions are going to compete. The ratio of the substitution product versus the elimination product is going to depend on the relative rates of those two reactions. So I'm going to have to do an analysis based on the type of substrate, the type of nucleophile or base. And I have to figure out whether I undergo substitution or elimination. So let's look at SN1 versus E1. Remember, they went through a carbocation, and how do I get a one versus the other? So if I have secondary and tertiary haloalkanes, and I have polar protic solvents, I'm going to get mixtures of substitution and elimination. These product ratios are very difficult to predict. So let's say I have iodine, which I know is a really good leaving group, or even chlorine, which is also a good leaving group. The first step is loss of leaving group. Here I have a tertiary carbocation, which I know is very stable. Well, I minus is actually a really good nucleophile. Chlorine minus is a good nucleophile. This is actually a very weak base, but I can undergo E1 to get the elimination. I can undergo SN1 if I'm in water where I get the alcohol, or I can undergo SN1 if I'm in ethanol to get this ether. So what I notice is the product ratio is going to be very dependent on what's actually happening. And many times when I go through a carbocation, depending on the nature of the base and the nucleophile, I'm going to get a mixture of SN1 and E1 products. Now, what about SN2 versus E2? It's much easier to predict the products ratio of SN2 and SN1. This is because when I have an attack of a base on a beta hydrogen by E2, this is only slightly affected by branching at the alpha carbon. The alkene form reaction is actually accelerated. So this is my beta hydrogen, and if these are carbon groups, remember my SN2 reaction is going to be impeded by branching at the alpha and the beta carbons, because this is driven by steric hindrance. In that case, when my alpha or my beta carbon is very crowded, this is more accessible, right? This hydrogen is more accessible than the backside of that crowded alpha carbon. So this will favor elimination. Steric crowding on the alpha and the beta carbon will favor elimination. Okay, so how do I figure out what's happening? I'm going to look at the type of substrate. If I have methyl or a primary haloalkane, basically, if I have a methyl alkane, I'm not undergoing SN1. My SN2 is generally the only substitution reaction. right? Because why? Because I can't form a double bond if I only have one carbon. So really I want to look at primary. Here, I'm never going to undergo SN1 or SN2. And that's because primary cations are never formed in solution. So SN1 and E1 reactions of primary are never observed. Okay, so if I have a primary alkyl halide, the choice is going to be SN2 and E2. Okay, so I will get SN2 as the main reaction if I have a strong base such as OS minus, OH minus, and BTO minus, so ethoxide or hydroxide. This is also going to be the main reaction with good nucleophiles, which are also weak bases, such as I minus and acetate anion. So SN2 will be favored by strong bases and really good nucleophiles, which are weak bases. E2 is going to be favored with strong, bulky bases. So potassium tert-butoxide. If I have tert-butoxide, this is really, really, really bulky. This is a bulky, hindered base. It really can't access the carbon in order to do. This is also considered non-nucleophilic, really, because it's really hindered, right? It's a bulky hindered base, which tends not to act as a nucleophile and more as a base because it's got this bulky alkyl group on it. So if I have that, my primary alkane will undergo E2. So if I have a primary haloalkane, I have to look at the base or the nucleophile. And I have to assess if I'm going to have substitution or elimination. I have to take another sip of my coffee, excuse me. Hopefully that will suppress my tickle. Okay. Now, if I have secondary, and it didn't, okay. If I have a secondary alkyl halide, if I have a weak base good nucleophile, such as I minus and acetate, all right, weak base, good nucleophile, I will get substitution. If I have a strong base, which is also a good nucleophile. So here's the difference. These are weak bases, these are strong bases. Oops. I'm going to get elimination. Now, if I have weak nucleophiles in polar protic solvents, such as water, methanol, and ethanol, I'm going to get a combination of SN1 and SN1 and E1. If I have a tertiary alkyl substrate, I never get SN2, right? Because I have this crowding at that tertiary carbon. So what I have to decide is, do I get elimination, which happens with strong bases, or do I have a poor nucleophile, which is a weak base, and that's going to give me SN1, a combination of SN1 and E1. So I only have E2 or a combination of the substitution that goes through SN1 mechanism and the elimination that goes through an E1 mechanism. So here's some examples, and this is where we're going to end this chapter. I want to predict the major product and the mechanism. So this is a tertiary alkyl halide. This is a protic solvent. High temperature favors elimination. And this is a really strong base, which is a good nucleophile. Excuse me. So if I look up here, the only choice I have is between E2 and SN1 or E1. Well, when I have strong bases, it's going to go E2. E2 is going to give me the Zaitsev, right? So this is going to undergo E2. It's going to give me the Zaitsev. So my double bond is going to be the most substituted double bond. And what I get is that as my major product. All right, primary alkyl halide, weak base, very poor nucleophile because it's a tri-substituted alkene. Moderate room temperature, aprotic solvent. So if I look at primary alkyl halides, I'm going to get either SN2 or E2, right? And what I'm going to get is the main reaction with weak bases is going to be SN2. So what I'm going to get here is going to be this quaternary ammonium salt because it's such a weak base. It's actually a poor nucleophile though, so that one's a little dicey. It's just amines are very weak bases, so I'm going to go with this answer. So this is going to be what did I say? There's going to be, with the primary, it's going to be SN2. All right, here I have a secondary alkyl halide. I have a very strong base. I have a very good nucleophile. And I have a perfect solvent. So when I look at my secondary, strong base with good nucleophiles, it's going to give me E2. So this one has to go through E2, and it's symmetrical. I'm going to get the Zaitsev, which means, actually there's only that one product that could form because those are equivalent. And I'm going to get the trans as my major product. Here I can form cis or trans. So I'm typically going to get the trans product so that those two alkyl groups are going to form far away. So I'm going to get the Zaitsev, and I'm going to prefer the trans as my major product. Now my second one, I have a secondary alkyl halide. I have a good base, strong nucleophile, or a strong base, good nucleophile, and I have an aprotic solvent. So when I look up here, again, my strong base, good nucleophile is going to give me E2. Doesn't matter what the solvent is, what I'm going to get is E2, which is going to be, this is going to stay the same. And I could either write this as going down or going up. These two carbons are equivalent. And they're symmetrical, so there's no Zaitsev, there's no regiochemistry. So this is the product that I'm going to get. So hopefully you understand that there's a lot of chemistry in these 52 slides, right? Which is why we spend a lot of time on this in class, because the key part is learning this material and then practicing and practicing and practicing and practicing and practicing and then practicing some more. So doing the homework, doing other practice problems, doing those activities that I put in the lecture module, those are going to be critical for success in this chapter. This chapter takes a while to grasp. There's a lot of nuance. There's a lot of chemistry that we've talked about pretty quickly. So what you're going to have to do is really focus on studying the outcome based on your analysis of the conditions and the substrate in order to figure out what's going to likely happen in these types of reactions. So I'm done with chapter 7. Now it's up to you in order to practice and to ask questions if you don't get something. So good luck. I'll see you in a bit.